In this video, I will introduce you to L'Hopital's rule, a really cool rule. First off, if the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals 0, and the limit as x approaches a of f prime of x over g prime of x equals L, then the limit as x approaches a of f of x over g of x is also L. The other part is very similar. If f and g both go to infinity, then you still have the same limit. So let's look at this as an example, because this is a theorem and it looks confusing, but it's not really confusing. Suppose we have the limit as x approaches 2 of x squared minus 4 over x minus 2. If you plug in, you get 0 over 0, which normally, before, we would have factored this and canceled, but this is a different way. We're going to do it a different way. Since I have 0 on the top and 0 on the bottom, I can do what's called L'Hopital's rule, which means I'm going to look at the derivative of the top over the derivative of the bottom. This is the notation I use for using L'Hopital's rule. I just think it's cute, because you can't really say it's equal until you find an answer, and then once you find the answer, then it's all equal, but you don't do it yet. So the derivative of the top is 2x, the derivative of the bottom is 1. Now when I plug in, I get 4. 4 is fine and dandy. That's our limit. Let's do another one. The limit as x approaches 0 of sine x over x. If I plug in, I get 0 over 0. So I can L'Hopital it, and I'll get cosine x over 1. Now when I plug in 0, I get 1 over 1, which is 1. So then my original limit is 1. So here we have the limit as theta approaches 0 of 1 minus cosine theta over theta squared. When I plug in, I will get 0 over 0, which means it's L'Hopitalable. So I L'Hopital it. And I get the limit as theta approaches 0 of sine theta over 2 theta. But wait, I get 0 over 0 again. No worries, we just do it again. So now I have the limit as theta approaches 0 of cosine theta over 2, which is good. The top goes to 1, the bottom goes to 2, which gives me an answer of 1/2, which means my original limit is also 1/2. This theorem only works when you have 0 over 0 or infinity over infinity. There are other indeterminate forms. 0 times infinity, what is that? We don't know. 0 times any number is 0, but infinity is not a number, it's a reality, it's a concept, it's funky. So I don't know which one has a stronger pull. Here, infinity minus infinity. See, there are different sizes of infinities. Which one is going to prevail? Is it going to be 0? Is it infinity? Is it pi? I don't know. It could be all kinds of things. Other indeterminate forms are 0 raised to the 0, 1 to the infinity, and infinity to the 0. This means you've got a function raised to a function where the bottom function is heading towards 0, if you've got 0 to the 0, and the top function is heading towards 0. So what's the solution? How do we do this? Well, we want to massage it so we can get it into one of these forms that we know. So let's take these one at a time. 0 times infinity. Let's look at the limit as x approaches 0 from the positive side of x times natural log of x. Positive side because you can't approach 0 from the negative side in the natural log. When we do this, I get 0 times infinity. When you have 0 times infinity, you're going to want to shove one of the functions to the bottom. Natural log almost never goes to the bottom. I'm sure I can find a counterexample, but right now I almost always never probably put it on the bottom. So I'm going to rewrite this as the limit as x approaches 0 from the positive side of natural log of x all over 1 over x. Now I've got infinity over infinity, I can L'Hopital it. When I L'Hopital it, I get 1 over x over negative 1 over x squared. Do a little algebra, so I get negative x. Now I plug 0 in and I get a 0. Seems kind of anticlimactic. Anticlimactic? Yes. So that's how you deal with 0 times infinity, shove 1 to the bottom. What if you have infinity minus infinity? Well, here's an example. You want to try to make it into a fraction. Try to massage it somehow so you can L'Hopital it. This is nice. I've got two fractions. I'll find the common denominator and bring them together. This gives me tan x minus x squared all over x squared times tan x. So I have 0 over 0, I can L'Hopital it, and I get a god-awful mess. I have secant squared x minus 2x all over x squared secant squared x plus 2x tan x. The top goes to 1, the bottom goes to 0. Oh crap! What do we do? When you see 1 over 0, you should think infinity. So especially if it's a one-sided limit. Notice at the bottom as x approaches 0 from the positive side, this will all be positive and this will all be positive. So the bottom will be positive as you approach that 0. So 1 over a quote-unquote positive 0 will give you positive infinity, which means my original limit was positive infinity. When dealing with these indeterminate forms, you pull the same trick. You've got a function to a function, so you're going to rewrite it as e to the natural log of that function to a function, because e to the natural log cancel out. Using my law of logarithms, that g of x comes out front of this thing, front of the natural log. So now what I care about is, where does this exponent go to? Let's look at an example. Let's say I have, as x goes to infinity, x raised to the 1 over x. This is the indeterminate form. Let's say I've got infinity to the 0. So that's this third one. I'm going to rewrite it as e to the 1 over x natural log of x and see what happens to that exponent. So the limit as x approaches infinity of natural log of x over x, I have the top going to infinity and the bottom going to infinity, which means I can L'Hopital it. The top becomes 1 over x, the bottom is 1. Now I can plug in 1 over infinity is 0, which means that limit is 0, which means my original problem becomes e to the 0, which equals 1. So the takeaway from this, if you have 0 over 0 or infinity over infinity, you can use L'Hopital's rule. If you've got 0 times infinity, shove one of the functions to the bottom. Infinity minus infinity, try to make a big fraction, jiggle it so that you have a big fraction so that you can get 0 over 0 or infinity over infinity. If you have one of these functions to a functions to give you one of these weird terms, you use the e trick. And that's all there is to it.